So we're gonna, at the end of the last lecture, this is sort of the midpoint of the slide set, the logistic model for matched data. We sort of very quickly reviewed at the end of the last lecture the sort of the EPI 534 approach to matched data analysis, which is the setup of sort of these McNamara style tables, these matched tables where you compute this matched odds ratio, which is really the same as the Mantel-Hansel odds ratio for stratified data analysis. And so we sort of mentioned that this was a limited approach to analyzing matched data. And so we're going to take it further today with how do we set up a logistic regression model to handle the matched data situation. And we talked about this sort of the endometrial cancer data set, which is sort of a classical example of a case control study. And this was 63 pairs of data. And the idea was to understand the association between supplemental uses of estrogen and development of endometrial cancer. And that's so the estrogen is the exposure, cancer is the outcome. And we saw that this was sort of the data layout here, where you had 29 cases that were exposed where the control was not exposed, compared to 3 in the reverse situation where the control had the exposure and the case did not. And we talked about how the odds ratio essentially reflects this tug of war between these two pieces of information. The 29 sort of supports the idea that exposure is associated with cases, and the opposite, that not being exposed is associated with being a control, and the reverse is in this cell here. And so the odds ratio is X over Y, reflecting this tension. And if these two cells are balanced, then we say there's probably no association between the exposure and the disease state. So that was the matched odds ratio, and we just very quickly just threw up the formulas for the 95% confidence interval and the chi-square 1 degree of freedom test for those data. And this has all been covered previously. So we say here that we have a wide confidence interval, but one that's sort of does not contain wall at 1, that's sort of positive on the other side of 1, and indicating a sort of positive association. And then we say that's highly, highly significant for the null hypothesis of the odds ratio equals 1. Okay, so this is last semester sort of thinking, and now we're going to move this forward here. So we talked about one of the limitations of this analytical approach, or sort of the stratified analysis approach, is that you're sort of stuck only really controlling for factors that you matched on. So if we, in this study, they had matched on age, marital status, and sort of a time variable, essentially, here, date of entry into the community. And that was sort of in the case control, it was in the sort of the control selection process, it was in the matching process. And so that you're controlling for in the analysis, but we talked about how other factors that you measure along the way, because you're going to measure a whole lot of other things in the study, you're going to have a questionnaire, you're going to take blood work, you're going to do a lot of other assessments, those don't really get to feature in the matched analysis. And that's a shame, because you may have potential confounders or effect modifiers that you collected along the way in the conduct of the study that you want to utilize. And so that's really the biggest argument for doing the logistic regression approach to match data. And so here in this example, gallbladder disease history, which it was an important potential confounder. And so this was again measured along the way in the conduct of the study, and it's something we want to control for. And again, we talked about last time that this is something that you needed to potentially interview or get someone's medical records in order to assess, and you couldn't match on it because you had to enroll them in the study in order to assess this thing. And so it's always, this type of confounder is always something that's going to come after the matching process. And so what you may get is a situation like this, where you have the data, here's your fake data, where these first 2 rows represent a case and a control pair. So this is pair ID 1. This is sort of an index variable to keep track of which pair we're talking about. And we know this is the case. Why do we know this is the case? Because they have D1 and then 0. So every pair is going to have 1, 0, 1, 0, 1, 0. That's sort of by design what the matched case control data set has to look like, if it's pair matched. And here's the exposure. This is sort of the thing of interest. This is the thing that's sort of left to vary that we're interested in, is how many are exposed or unexposed. And then here is this other piece of data that we collected along the way, the gallbladder disease status. And the reason, again, we can't control for this in stratified analysis, sorry, I'll pop that up. The reason we can't control for this in stratified analysis is that if we wanted to control for gallbladder disease status within a matched pair, imagine you're doing a stratified analysis of these data, which is what we're essentially doing previously. There'd be a table with just two people in it, these two folks, and we wanted to control for gallbladder disease status, and we'd have to, according to how stratified analysis work, you'd have to make two tables within this table that only has two pieces of data, and you'd have to stratify further by the gallbladder status, and then you'd make two tables, each with one person in them, and that wouldn't work. You can't have a table with, you can't split your table out further when there's only two people in it. And so we have to use another analytic technique, which is going to be logistic regression. This just said what I said. Okay, so if these are discordant, you couldn't even use them in a stratified analysis because you'd have to break up these tiny, tiny tables with only two people in them. So what we're going to do is sort of retool how we write our EVW model that we talked about last week and before to really define sort of distinguish between two different sets of V variables. So we have our usual disease and exposure status here. But we're going to now not just have what we used to just be called the V's, which were the potential confounders that we measured for our study, but we're also going to keep track of the fact that of another type of V, which are really the dummy variables that indicate which match set we're looking at. So what I mean by this is these V1s are this variable here, essentially, pair ID. Because in this analysis, just in the stratified analysis, we had to stratify on pair ID. That's what you were doing in the McNamara approach. You had essentially summarize all the data within every stratum one by one. So you have to go you'd analyze this table, and then you'd analyze this table, and then the collection of that is the Mantel-Hansel procedure. So in the logistic regression model, we're going to need to essentially input that variable, and we're going to call it the V1s. Now, if we had, on the previous slide, pair ID went 1, 2, 3, 4, and so forth. In the logistic model, we're going to have to put those in as dummy variables to represent all of the values. So if there's 100 matched pairs or 63, let's say there's 63 matched pairs, which is in this situation, you'd have 62 dummy variables to indicate which sets we're talking about in the analysis. And again, you need a control for this, because this is sort of the key thing that keeps track of the matched sets. So we have two different types of V's. These that keep track of the matched sets, and then other sort of more traditional confounders. And then there's potential effect modifiers. And really, the ones that we're talking about generally are going to be the effect modifiers that involve these V2s. Okay, these are, because these dummy variables for the matched sets aren't really interesting in terms of effect modification. Do you care if there's effect modification by whether you're in match set 10? It's sort of an odd thing to keep track of. So this, as an effect modifier, is sort of strange. But for these, please imagine this is gallbladder disease history, then that might be an effect modifier that you may want to look at as a W term and an EW term. So we'll show that. And so with this type of model, we can rewrite our logistic model by essentially distinguishing between the V1s and then the V2s. So the old way we had last week was just we had all these gamma times V terms, and then we had our E times delta W terms, and now we're going to split out the V terms into two types: the ones that keep track of the matched sets and the ones that keep track of the more standard confounders. Okay, so again, slight tweak to what we were doing before. And really, not much changes in terms of thinking about the odds ratio. We wrote the model a little differently, but really, things don't really change too much. So, so here is the logistic model for a matched analysis of case control data. We have these sort of V terms for the matching factors, but otherwise it looks sort of the same. Now, one thing to keep in mind, this is sort of the crazy thing about odds rate or about the case control design, and is sort of talked about in the other courses before this. So I'm not going to go into all the reasons why, but what sort of might strike you as odd about this model is what is the outcome of this model? What's sort of on the left side of the equation? Disease status, right? This is the probability of disease. This is the logit, or the probability of being a case, essentially. And on the right side is the exposure. And that's sort of weird if you think about what a case control study is, right? Because the case control study, the outcome is sort of the exposure, right? You're sampling based on disease status. You say, I have cases, I have controls, and I want to see who's exposed. And that's right, so it's sort of a reverse study. And yet, we're actually writing the model with exposure on the right side of the equal sign. So we're writing the model exactly the same. Okay, so this is just an odd, it may strike you as strange, but it works out, and this has to do with the exposure versus risk odds ratios and sort of some of the cool results about how you can flip the results of a case control study that I think is probably derived in 534 in the spring. But it is a little strange because the disease, we know exactly, if we have a pair-matched case control data set, we know exactly that half of the rows of data are going to have a 1 for disease, and the other half is going to have a 0. We've exactly sort of defined what the prevalence of the disease in the data set is. All right, and that's just sort of, so it's sort of odd that this is the thing that sort of freely varies as the outcome. But again, it still works out from an analytical perspective, but just something to keep track of. So again, so here's sort of our logistic model. It looks very similar to previous models. We have our EW terms here. Again, these W terms are probably only going to contain these are really going to only be defined in terms of these V2s, because these are sort of real confounding variables that we measure. These are just sort of bookkeeping variables for the strata. And the odds ratio is exactly the same expression for the odds ratio as we saw before, and that's because all of the V terms drop out in our expressions for the odds ratio for exposure. That was true when we had one type of V, and it's true when we're going to have two types of Vs. It doesn't really matter. All of this sort of just cancels out in our expression for the odds ratio, and we're still stuck with just the W terms in the exposure odds ratio. So the question is sort of how do we apply this model? So there's sort of the one other switch that we're going to make is that our usual way of doing business, which is the unconditional logistic regression model, isn't going to quite work for the matched analysis situation. And so here's sort of an overview of sort of two approaches to analyzing these data here. And the traditional way that we would go about things, which we talked about previously, is sort of the unconditional logistic regression model, which is the usual way of estimating our parameters. And it's really only designed to work in a situation when you have the number of, here this is P, means the number of parameters, is small relative to the sample size, or the number of outcomes, however you want to think about it. And so here's a traditional sort of study, let's say it's a study without matching, and you have 200 subjects, and you measured some covariates like age, race, and sex, and here's just a hypothetical model with 5 parameters. This is a situation when you want to use unconditional logistic regression. But what we have going on in the situation where we have a matched analysis, this really doesn't work out so well. And the problem is that if you had the model that we had, if we have this model with all these V1s, and you try to fit an unconditional model, you're going to have a problem. And the reason is if we have 200 subjects and it was a pair-matched study, you'd have to put in you'd have to keep track of 100 strata, 100 matched pairs, as in terms of V1s, and there'd be 99 dummy variables. And that would be really bad. Just say it'd be really bad. Proc logistic will not work. It will not give you answers that make any sense if it runs at all. Because you'd have essentially, you'd have 99 dummy variables and you'd have an intercept and an exposure. this exposure term, and basically you cannot estimate that many terms relative to the sample size, and it just won't run. Right, so you need to control for the match sets. You have to do it in order to get the right answer, but it's not going to work. And so instead what we do is something called the conditional logistic model, otherwise known as stratified logistic regression. And you'll see that in the SAS code, we're actually going to use the statement that's called the strata statement, because essentially what you're doing is sort of like a Mantel-Hansel approach, where you're analyzing within each match set some information. And the logistic model is essentially computing its estimates from within the match sets. And we use this in situations where we have a large number of parameters relative to the sample size. Okay, so this is again often in matched analyses. And so, for example, here we have, imagine you had a pair match version of the same study where you matched on age, race, and sex instead of controlling for them as covariates. Here, if there's 200 subjects, you'd have 100 matched pairs, and your model might look something like this. Alpha plus beta times exposure, and then 99 dummy variables to keep track of 100 matched pairs. This is a situation where you need to use the conditional logistic model. So you might say, well, where's sort of the threshold where I say I have too many parameters for unconditional versus conditional, and there's no sort of answer to that. But for a matched situation, you really need to use conditional logistic regression because you're going to have a zillion dummy variables, and you will not be able to fit your model. And we'll sort of go through what this looks like on the coming slides. I will say just one thing is that you will get, see, it says bias potential. If you try to fit this model to, an unconditional model to pair match data, if SAS runs, you will get the wrong answer. So that is just, it will not work out well for you. And your estimates will be biased, and we'll talk about that in a moment. I will say that conditional logistic regression almost always leads to less precise answers. So you'll have wider confidence intervals in a conditional model. If you fit the same data set, imagine if you didn't have pair match data, and you just had a more standard analysis, you might be able to fit a stratified or a conditional model to a standard data set. You will always get a wider confidence interval than the unconditional model. And that is because this is essentially looking within strata and it's sort of slicing and dicing up your data set in a way that the unconditional model is not. So, but then it says here in parentheses, this is just something you should always appreciate in life as an epidemiologist, that you should want to take a wider confidence interval if you get an unbiased answer, right? Hopefully, I'd rather be less precise around the truth rather than precise around the wrong answer. So that's sort of, maybe you philosophically differ, that's sort of my mode. I'd rather be uncertain around the truth. And so that is just something to keep in mind here. I was trying to think of the right, political presidential race, allegory here, being stretching truth and bias, and it didn't come to me. So, insert presidential race joke. Because I think there's been by various metrics of truth, this has been the least truth-based or reality-based presidential season. So, I don't know. Sorry. My political opining will get more intense as we get closer to November. So bear with me. So something to keep in mind here. So the conditional versus unconditional models here. So this is just sort of getting into the issue of bias here. So if you imagine you had a pair match study with N0 pairs here. Okay, so some number of pairs. This is, so you had 63 pairs, N0, then you'd have, twice as many, 126 people in your study. And you had this model here. This is the model, a simple model that only controls for exposure and the matching variables. This is a simple model for matched analysis. It's only got V1s. And all you're doing is looking at the exposure-disease relationship, controlling for the straight up. And this is sort of exactly what would you sort of expect this to sort of equal in terms of the odds ratio? If you just fit this model, you should get something that's hopefully exactly like the McNamara base or the matched odds ratio, right? Because all you're doing is controlling for the strata and looking at e to the beta in this model that should hopefully get you the x over y answer. If it doesn't, we should talk. But this should work. And so in this very, very simple model, if you fit a conditional logistic regression model, you're going to get your e to the beta is going to give you the sort of appropriate answer, right? The odds ratio is going to be equal to e to the beta. But what happens is if you fit the unconditional model, so let's say this was 100 matched pairs, so there's 99 dummy variables, and then you have an alpha and a beta, that's 101 terms in your model, and you fit an unconditional regular logistic model, you're actually not, if SAS runs, which it may not, if it does run, it's actually going to also give you the wrong answer. It's going to give you the square of the correct odds ratio. This is the bias piece. Not only shouldn't you have done it, but you might actually get the wrong answer out. And so, for example, if the correct sort of unbiased answer was an odds ratio of 3, you're going to get an odds ratio of 9. Okay, so this is only in the pair match situation. The bias is less predictable if you don't have pair data. But basically, you can sort of prove algebraically that this will happen. You don't even need to run SAS to determine this. It gets a little crazier for other data. So if you have pair match data, you not only should not, from a SAS perspective, run the unconditional model, but you'll get the wrong answer. So we're going to sort of just look at what this analysis looks like for the endometrial cancer data, where again we want to control for gallbladder disease history as a V2, so just a regular old control variable. Before matching, just a regular control variable, and then we have all these V1s. We have 62 V1s, right? These dummy terms to represent 63 pairs. And all of this match stuff is sort of baked into that, right? We have age, marital status, and date of entry. They're sort of part of the matching process, and they're all sort of jointly controlled for in this pair ID variable, right? We can't distinguish any of this. We can't distinguish the individual contributions of these matching terms, but because we matched on them, they're all sort of all in the process, and they're sort of all that information is being controlled for in pair ID. Okay, so this, again, we're sort of perfectly balanced on these factors through matching, and sort of in there. So again, these are the V1s and these are the V2s. And again, so we want to fit the conditional logistic regression model here, because why? We have 126 observations, right? 63 cases, 63 controls. And we've got, in this model, we've got 62 dummy variables, right, plus this term for gallbladder, that's 63. And then we got intercept and beta, and the beta term here for exposure. That's 65 things to estimate out of 126 pieces of data. That's asking a lot. And so we need to use the unconditional model, okay? And in theory, if we fit this model using the conditional model, e to the beta really should be our odds ratio, right? Why? Because we know that there's no W terms. We just got two types of V's, and V's cancel out in our expression for the odds ratio for exposure. And so what's left here is just e to the beta. And so if we fit this model, e to the beta should give us the association between estrogen use and cancer. Okay, so we could imagine some other slightly more exotic models, right? One that involved effect modification. Probably, again, as we said, with the non-matched V's, it's pretty weird if you had exposure times pair ID 22 or whatever. Just an odd thing. And so here we have V2 for gall, we have sort of a single V2 term, and then here's sort of the interaction term between exposure and gallbladder disease status. So this this sort of makes sense to have this sort of effect modification. This, not so much. Okay, and now the exposure, the odds ratio for figuring out the effect of exposure right now necessarily involves this EW term. Right? As we talked about before, the EW terms are part of our odds ratio expression, and this makes sense, right? That the effect of exposure, or the association between case control status and exposure, is going to change based on their gallbladder disease status. That's exactly what we're saying here. And so now the odds ratio expression reflects that. Okay, so again, this is all principles we saw before, and the only new piece here is that we now are explicitly representing the matched variables as variables. This is exactly stuff we saw before. So, okay, so here's, again, what our data layout looks like. This is very similar to what we saw before. This is sort of what a real-world data set would look like. And I sort of divide it into nice, required, and optional. And the reason is that this is sort of the bare bones for a matched analysis. You need to have something that represents the matched pairs, 1, 1, 2, 2, 3, 3, whatever you want to call it. Right? This is going to represent the households, the twins, the case controls, whatever you want it, whatever it's going to be. And you need to have their disease and exposure variables, right? This is just their study IDs, right? These are two different people, 1, 2, and 3, 4, and so forth, right? In the actual conduct of a study, you're going to hopefully keep track of individuals. And so right, these are actually different people, and so you hopefully have a study ID variable because you're going to merge in other data on these folks, and you need to keep track of who's who. Okay, so it's really more than nice. If you don't keep track of your participants, you haven't done a good job. So please do that. And then you have these optional variables here on the right, which really represent sort of the other stuff you measured in your study, right? The gallbladder disease status, smoking, various blood work that you did, whatever it is going to be all these other variables in here. And this sort of double data, this sort of 2 rows per pair data set represents your analytical data set. And you've got to have the pair ID. Okay. So again, we're going to have 126 observations for the endometrial cancer data. And this is really what you do. It's a slight modification to your logistic code, okay, where you essentially, you have your standard model statement, but now you have something called the strata statement, okay? And this is essentially telling SAS to fit a conditional model. When you put the strata statement in, you're saying, SAS will switch its output. It'll actually say, I am running the conditional model, not unconditional. It'll have, say, running conditional logistic regression. And what it's doing is it's essentially fitting this different likelihood that is stratifying on the pair ID. And it's modeling, it's not including, even though we've written out pair ID in the model over here as part of the equation form of the model, it actually is it is not appearing, the pair ID does not appear as a traditional covariate on the model line. Okay, so that's sort of the key piece here. It is not going to appear in any of, not only is it not going to appear on the model line, it's actually not really going to appear in the output. So you're going to get results out of SAS that are going to tell you about EST, that's the estrogen, that's the exposure, and then gallbladder status. It's going to give you output for it. It's actually not even going to give you output of much interest for pair ID. And that's because you're actually stratifying on it. It's not really something that's in the main part of the modeling, and it's fitting this conditional likelihood. And you're only going to get output on the other stuff. And that's actually sort of good. You don't care about the pairs themselves. There's nothing interesting about pair 62 other than you need to control that they are pair 62. You actually don't care about that, sort of estimating the effect of pair 62. It's sort of uninteresting. It's this nuisance thing that you want to get rid of. And we'll see that in the output. So really the only thing we do different here is we have a strata statement that names the variable that you're stratifying on. All right, that's it. And then SAS sort of knows to switch the hood on the estimation process. See, and it says conditional analysis. So that's all the fanfare. And again, so what you see here is in the conditional analysis, we are stratifying on 62 strata of these pairs. And again, the output only has est and gal in it. So the V1s don't show up in the output tables. And you get you can get your traditional MLEs here, these your beta estimates, their standard errors, the wall tests, as well as you get the typical sort of e to the betas table, the odds ratio table. So you get all of your standard stuff. The key piece here, is that what disappears is the pair IDs. So essentially, imagine you're just like if you fit the Mantel-Hansel procedure in Proc-Freq to matched data, which is something you did last semester, you get zillions and zillions of tables, right, representing the analysis of many pairs of data, and at the end it gives you a Mantel-Hansel summary statistic, which is also equal to X over Y, the matched odds ratio. This is essentially doing a stratified likelihood approach, and it's making many virtual tables for every pair ID, and it's estimating the beta sort of across all of those tables. It's stratifying in a way that's very similar to the way that you stratify to get a Mantel-Hansel odds ratio. And it's doing all that under the hood when you put in the strata statement. So these are in our representation of the model, but they're not actually in how SAS fits the model line. Okay, so there's actually this is just another way to this is just something to know. This is not something you're probably going to do very frequently. It used to be that before SAS added the strata statement into Proc Logistic, which came out, I don't know, SAS 9.1 maybe? I think in 9.1? I don't know. Before that, you used to have to use Proc PH-Reg to fit the matched analysis for the conditional logistic model. So which is actually PH-Reg you're going to see soon. It's going to become your friend because we're going to do survival analysis using the Cox model in PH-Reg. And anyway, before SAS had the strata statement, you had to use PH-Reg. And there's sort of a different way to lay out the data and sort of to do that analysis. And there's sort of another way to, if you have sort of frequency-based data, like here, imagine this situation is 27 observations where you have a case and a control, and this is their exposure status. You could this is sort of similar to the event trials format. The point is there's sort of other ways to do this in PH-Reg that don't quite work in strata, so with Proc Logistic. So just, you cannot fit, the point of this slide really is if you have sort of event trials or frequency-based match data, you really can't fit it in Logistic, and you have to still use PH-Reg. And so when in most of your career, you're going to have individual response data. But if you have aggregate data that's matched, you got to use PH-Reg is really still the story. The strata statement has to have individual line listed data. Small aside, if it ever comes up in your life, remember this slide that you have to use PH-Reg when you have the group data. So that's really just sort of the overview here. Of what we do for the conditional model. Really, it's just a slightly different representation of the model where we have the V1s, we fit the strata statement, and then you're going to get estimates that leave out pair ID, and you're going to get sort of only the V1s are going to be represented here. The V2s are going to be represented in your output. And that's just what it is. These MLE estimates are different than what you would get from a conditional analysis. If you didn't even have to worry about the bias, that squared issue around fitting the wrong model, the conditional results are going to always have less precision than the unconditional, and so you're going to get wider confidence intervals from this analysis, but you'll actually get the right answer. So again, something to keep in mind. We sort of, at the end of this slide set, I'm just going to run through just a very few, just sort of a few other things to keep in mind with matched analysis, just some other derivative issues that you need to think about when you're setting up your model for the conditional logistic model. One is interaction. I said before that we didn't want interaction or effect modification with the matching variables because I said that was sort of strange. But I just wanted to spend a moment to talk about ways where you think might be able to look at this. And so I'll talk about this. So interaction involving the E1s, the V1s. And so here, for example, if you matched, this is something we talked about two lectures ago. If you did a study where you matched on sex, age, and race, right, you might get a situation like this, where you have a case and a control that are similar on, these are both women, they're both green, they ride skateboards, that's supposed to be the young group, as we talked about. If you had a data set that looked like this, where you had cases and controls that are matched on these three factors, if you wanted to actually analyze the disease-sex association, you can't, right? This is this idea that we talked about. If you match on a factor, you can't really look at it. You can't include it as a factor in the analysis, right? Because if you wanted to look at the disease or the case, sex association, you might do a stratified analysis that looks like this. And basically what happens is that in every matched pair, they have the same sex, right? So in pair one, they're both female. Pair two, they're both male. So when you perfectly balance the data through matching, you really can't look at these, you can't look at associations with the matching factors by design. So if I fit a model where I matched and I controlled for pair ID and I also put in the model sex, it's not going to work. Like even if I have a conditional model and I say V1 is pair ID and V2 is sex, SAS is going to get really upset because it's not going to find any discordances in these tables. It's going to say, look, in every match table, they're either always male or always female, and it's not going to get you an estimate. It's not going to work. So this is this idea that once you match on something, you can't deal with it in the analysis, right? Another way of thinking about it is that if you sort of summarize these tables, you'd get the matched table, the McNamara sort of table would look like this. You never would have an X or a Y value. They're always concordant for the factor of interest. So you can't analyze it. Can't do it, don't do it. Won't work. Okay, so this just sort of says what I just said. You can't estimate the relationship between disease and the matching factor, but it doesn't necessarily mean that you can't look at interaction between sex and between the exposure and sex. So sort of the effect modification. This sort of rules out the case control and C relationship, but it doesn't quite rule out interaction. Effect modification, where exposure sort of changes, the relationship between exposure and the case control status changes across Cs. Okay, so for example, what if the exposure case relationship changes by sex? That actually is not ruled out by this situation. Okay, so for example, you might have data that look like this. So say, what about the E by C interaction or effect modification? Does the case control and exposure relationship change across values of sex? That's sort of theoretically possible. So imagine you had pair one where you have, let's look over here. We got a female match set. This is pair ID 1. Here we go. Let's put it all up here. Here is pair ID 1, females, where we have the control is exposed and the case is unexposed. And look at the other female pair. We have a control also who's exposed and the case is unexposed. So for females, you might start to make a table that looks like this. Okay, you got two females in the Y cell, where you basically see there's a negative association, right? The females are both female controls, pair IDs 1 and 3. The controls are exposed and the cases aren't. And the males in the study have the opposite, right? Where there's the case, these are the males so far in these three pairs. The males are exposed and the control is not. So you may actually start to see the signal of effect modification, where depending on which sex, we're talking about the exposure-disease relationship is different. Here, it's a positive association. Obviously, there's like no data. We only have one pair. We have one male, sort of one male pair in this cell, and we have two female pairs in this cell. But you actually could have effect modification on factors involved in the matching. Right? That's a real thing that could happen, even though we said you couldn't look at whether sex was associated with being a case or a control. Sex could still modify the exposure-disease relationship. Okay, so that's sort of the motivating issue. So the question is, this is possible, but what do we do about it is sort of the next layer, because there's sort of some complications from a modeling perspective. Okay, so it's possible, but what do we do? And so what are our options? This is the what do you do slide. What do we do? And so we have a few options, and they're all there's problems. One here is that here's a little more of a complicated model. What if we tried a model that looks something like this? We have the V1s and the V2s as we did before, so dummy variables for matching. Okay, these are the dummy variables for other potential, or variables for other potential confounders, the V2s. And now, we might have two types of effect modifiers. The ones that were the ones we saw previously, that we're now calling them W2s, that were effect modifiers involving the V2s, the non-matching confounders, so other gallbladder disease status, whatever it is. These we're okay with. But you could imagine making other terms for effect modifiers that included things you matched on. So for example, you could put age or sex in here as effect modifiers in your model. Okay? And so that is potentially something that you say, okay, this in theory the data might support you doing something like this. And now you might put age and sex in here as effect modifiers. Okay, but there's a problem. Please don't do this. Okay, this is what this means. Don't do this. Okay, this should strike you as sort of a strange thing to do. Okay, and the reason it's strange is I said you're going to put age or sex in here as an effect modifier or an interaction term with exposure. But age and sex were part of the matching process. They're not actually variables in your data set, and they're not really individually found in the model. I already said you couldn't put sex in as a V term because I said you couldn't look at the association between sex and disease. It doesn't work. The model will not support you putting sex in here as a standalone factor, as a V term, because you can't actually look at its association with disease. Okay, so the proposal was to put age and sex or whatever it is as effect modifiers here, but they don't appear on their own in the model. They're only inside of the matching variables. They're inside of pair ID. They're inside what it means to be pair 52. But it's not actually appearing on its own in the model. Okay, and that's a no-no from a modeling perspective, and this is something that was covered in linear regression, is that when you put interaction terms that are higher ordered two-way interaction terms, so exposure by sex in the model, you need to have exposure and sex alone in the model in order for the model to sort of be okay. And by okay, we call it hierarchically well formulated. That's sort of the phrase that means you need to sort of, if you have a higher order term that's, two or three-way interaction, you need to have all of the lower order pieces in the model in order to get valid results for your model. And so by this proposed idea sort of made sense because you'd be able to look at that exposure by sex relationship, but because sex can't actually appear on its own in the model, this is not going to work. Right? It's not even that, I'm faulting us for not having sex in the model. If you put sex in the model, you're going to get a crazy value because there is essentially, you're going to get a meaningless value because it's essentially perfect. There's by definition no association between sex and the disease outcome. There is no, because we matched. So this is just something, it's in theory a good idea, but we can't actually do it, or it wouldn't be a valid model to run. So the other piece here is you could potentially put another type of term in here, which is something I already said wasn't really a good idea anyway, which is you could imagine making dummy variables that represented the interaction with matched sets and of the matched sets themselves. So here, these are different W1s, where these are now effect modification terms defined in terms of the dummy variables for the strata, the V1s. Okay, so now you're saying V2 times exposure is an interaction term in the model. And that, again, or V52 or V100, or whatever it is for the matched sets. And that's just sort of an odd thing, because what is it really, we don't really care about a specific matched set's interaction with exposure. That's just sort of an unimportant thing. So the problem with this approach is that if you directly put the pair IDs in here as interaction terms, how do you interpret, how do you deal, what does it even mean? What if you matched on several variables at one time and you found that pair 22 or house 22, the exposure disease relationship or the exposure case control relationship in that household was different than the other households? It's hard to interpret it, particularly if you matched on, if the matching process is complicated. Household, how do you interpret a household? Or what if you had matched just on several demographic features? It's very, very hard to interpret what a significant term like that would mean. And so the other issue here is this is sort of, if you have a lot of matched pairs in your analysis, then this quickly becomes a lot of terms, or matched sets in your analysis. This quickly proliferates the number of terms in your model even more, and you're going to have a problem. And the reason is that when you do, if you had this type of interaction term in your model, in a conditional model, these have to go, these EW terms have to go on the model line, not on the strata line. And if you do that, it's going to really blow up the number of terms in your model in a way that we said we didn't want to do that earlier. So anyway, the point is there's really not a good solution here, even though in theory we think that there could be effect modification on the matching factors. It's sort of a challenging, there's sort of no easy way to control for it in the conditional model. These are sort of two approaches, they're both sort of flawed. So just a quick note on ignoring matching. Don't do it. Somebody will encourage. And so what I mean by that is you really have to so you might say, that last thing about effect modification was really demotivating. I wish we didn't have to even control for these matching factors by controlling for pair ID. That would sort of solve maybe some of the issues, at least with that model too. And the problem is it's not going to really work out so well. So, what if we matched on factors like age, sex, and so forth, and then when we did that in the design stage, and then what if in the analysis stage we sort of don't include them exactly the same way? And so, what if we said that was an issue of study design, but we do something different in the analysis? And so, what if in the case control study, we talked about this a lecture or two ago, in the case control study, if you ignore the matching, you're going to get an odds ratio that's biased towards the null, and you're going to lose precision around your risk ratio. This is supposed to say odds ratio. You might lose precision also as well if you don't control for the matching factors, the variables. In a matched cohort study, you lose precision by not controlling for the matching factors. So if you ignore the matching, you're going to get a downward biased estimate in the case control study, and you're going to lose precision in both designs. So you sort of need to, if you did a match study in the design phase, you sort of need to do a stratified or some sort of matched analysis downstream in the analysis stage. So, so something to keep in mind. There's also another bullet here that says, one thing you might be tempted to do, but it's still wrong, is you could say, what if I matched on age and sex, again, and then just included them as regular control variables? And that's again, something we said that doesn't really make sense because we sort of fixed them. We balanced the sample sort of already on age and sex. You need to really keep the analysis as stratifying on variables that indicate which pair, on the pair IDs or on the household. So you've got to do it. The other piece here is on breaking matching. And this is something that, here I'm just going to put the whole slide on here. You could, sort of, okay. So you could say in the breaking the matching, you can analyze the data that somehow accounts the matching factors but isn't a matched analysis here, which is something that we talked about. This is a variant on what I just said you shouldn't do. So this is another way of doing something you shouldn't have done, which is if you somehow you control for age and sex as V's in the variable, and you can still group the data into strata formed by sex and age and so forth, and there is still a way to analyze the data in terms of the pieces that went into the matching rather than the matched sets themselves. And there's an example here that sort of works out that depending on how you control for age, this example was sort of different ways to control for age, you could essentially break the matching, which means not analyzing on pair ID or on household ID, but you could sort of group the data by the factors that went into sex or in this case age. You can group them by different age groups and do an unmatched analysis just controlling for age. And then the short story here is you get different odds ratios depending on how you define your age groups. And so this is again another version of saying if you do a matched study, you've got to sort of do the stratified matched analysis as the outcome. So again, these are just some specific issues here that if you do a matched analysis, you've got to be a little extra thoughtful about your covariates, how you use them, and how you use the covariates that you measured, that you put into the matching analysis versus the covariates that are part of the V2s, all the other things that you want to control for in your model. And there's those covariates are treated very differently and very purposefully. So I think we're ready to trade off here. You ready? Okay, very good. And do you want modeling strategy? You want modeling strategy? All right. You're good.
Hello. I don't know if you followed all that because the last 10 or 15 minutes went pretty fast, although we recognized that you sort of had this topic covered in Lauren's course last spring. So I don't know if it was a repeat. I don't know if she covered all the things about matching. So, but what we're going to start to do now, I don't want to go over the things that Dr. R just finished. I want to start this new area, which is the sort of the new part of the course now, having to do with what's called modeling strategy. So we're now starting something that wasn't discussed, I don't believe discussed in any other course that you've had up to this point. Now, I don't know for sure because in the course you had with Azar, did you all take Azar last spring, the BIOS 591P, I think is what the course was, and he talked about linear regression, right? And so he didn't. I don't think he talked about logistic regression in that course. But when he talked about linear regression, somewhere or other, you had to learn how to fit linear regression models using PROC-reg, I think is what you used, PROC regression. And I don't know to what extent Azar talked about, well, if you've got a complicated situation where you have a lot of variables, different types, how do you not only do you fit a model, well, how do you determine with all the different variables you're working with, what's the best model of all the variables you're dealing with? And he might have said something about that, but that's what we're going to talk about now. That's what I mean by modeling strategy. What I mean by modeling strategy is, suppose you want to do logistic regression. I mean, let's keep it to logistic regression. Suppose you have a study and you know you've got enough variables and enough data and that you have an exposure variable, you have a health outcome, and you have a bunch of variables you want to control for, and you know you want to do logistic regression, and you even want to consider a model that considers confounding and considers product terms, interaction, and might even want to consider precision. Precision has to do with what? Precision has to do with the confidence interval that you're estimating around the odds ratio. You want to have a tighter confidence interval, as tight as you can. Suppose you have that situation and you're starting out with a model that has all these variables in it. Well, what do? Do you just fit one model? Do you just do that? Do you do something that you might have learned in the course, in Azar's course? There's something called backward elimination. Did you learn about that? What was backward elimination? What was that? That was when you start with this model, as big as you start with, and then you sort of do some significance testing to reduce the model, right? You get rid of things that aren't significant one step at a time, right? Now, there's a problem with that. Now, I don't know exactly, but we're going to talk about it in this context. A problem with that is if you do that, treat all the variables the same. You treat the interaction terms, the product terms, just like you're treating the E variable, the exposure variable, and just like you're treating the V variables, the potential confounders, and then you treat them all the same, and you let whichever drop first that's not significant in backward elimination, you're not doing something right because you're not considering the roles that the variables are playing. Should you allow yourself to drop a confounder before an effect modifier? Well, that's what we're going to be talking about here, is how do you go about the process of coming up with the best model, considering that when you're doing epidemiology, you have an EVW model typically that you want to deal with. Now, you may have something even more complicated than an EVW. You may have more than one E. We've only been talking about one E so far, but that's what we're going to do. Now, what I'm going to be doing in the next couple of classes, it's going to be 2 or 3 classes, and it's going to carry over to the rest of the course, even when we do other modeling procedures. I'm going to be talking about modeling strategy guidelines. You see, the word guidelines means we're not giving you a mathematical formula to tell you how to come up with the best model, because there's no formula. It has to do with an approach to how you come up with dealing with this complicated situation with all the variables and maybe this big model or some model you want to use to consider this, to come up with a final model that you think evaluates what you want to evaluate. So we're going to be talking about guidelines for how to do this, not a specific rule. And in fact, the guidelines are going to involve 3 stages. 3 stages, which I'll talk about hopefully before I quit today, a little bit about what the 3 stages are. And the goal of this set of guidelines and the 3 stages is to come up with what I wrote here is a valid estimate of the exposure-disease relationship. What does that mean? Valid estimate of the exposure-disease. It basically means you're going to come up with the right answer to answer the question that you originally asked in the first place. To what extent is the exposure determinant of disease? Or what's the odds ratio or the risk ratio, depending upon the study you're doing, that relates to the exposure to disease? How significant is it? And how precise is your estimate? So basically, you want to come up with the right estimate. Okay, that's the goal of this modeling strategy. Now, there is another goal. But that's not what we're going to be focused on. An alternative goal might be just to be able to get the model that allows you to predict the outcome as close as possible. It's a different goal. It's not to get the exposure to disease odds ratio or risk ratio. It's to try to actually use whatever is in the model as X's to get as close to what the Y is or the D is, the disease outcome is. That's a different goal. That's called a prediction goal. And if your goal is prediction, there's different approaches to that, different from what we're going to talk about. And actually, the approaches that describe prediction goal, the prediction goal, are in that book by Kleinbaum, Cooper, Nizam, and Rosenberg. There's a couple of chapters in there about how to deal with the prediction goal. We're going to be talking about the validity goal. of coming up with a, now, another thing I say on the slide, at the bottom of the slide is, you also got to realize is once you go through this process of coming up with what you decide is the best model that eliminates some variables, that considers interaction, considers confounding, and consider precision, you got to do one last step. One very important last step is what you got to do is decide something about your original question, about the exposure-disease relationship. You have to evaluate that. You don't want to just get the final model and then let go with what you originally were doing the whole thing for. So you want to come up, so what do you want to do? So basically what I said, you need to draw conclusions about the exposure-disease relationship. And that typically involves assessment involving statistical inference and even involving clinical significance. In fact, there are typically three, as far as statistical significance, there are typically three things you want to get at the end of this whole process of coming up with the best model. You want to get three things. You want to get a good, proper, appropriate estimate of the measure of effect that you're studying. If it's logistic regression, the classic measure of effect is the odds ratio that you're going to get. You want to get a good answer for the odds ratio from your final model. You want to get what's called a point estimate. Remember that terminology? You want to get a single number. The odds ratio is 4.2. The odds ratio is 15. The odds ratio is 1.7. You want to get a point estimate. What else do you want to get? There's two other things you want to get. You want to get a confidence interval around that odds ratio. What's that going to do? That's going to tell you about how precise is your estimate. You want to know that because if it's not very precise, you can't, if the estimate is 4 and the confidence interval is all over the place, you're not going to feel that comfortable with the estimate. So that's the second thing you want to do. What's the third thing you want to do? You want to decide whether you think it's statistically significant. Now there are different issues involved in this, but you basically want to know whether the result could have happened by chance, or are you testing a null hypothesis? And you want to see if the odds, so there's three things you want to do. Test of significant, a confidence interval, and you want to get a point estimate. So all of this is the final part of the strategy. Now, here's a couple of pictures. Okay. Do you see anybody on this slide that you recognize? Let's see, this guy, and this guy, this is me. This is like, as I said, circa 1980. Oh, man, I was, look at the beard. I was worse than this. I mean, there was one point I got a teaching award, and I didn't realize how much I looked like Charles Manson. This is not even close, okay? This is my colleague, Larry Cooper, and he and I were the two original, longtime friend and co-colleague. We were the two original authors of the book that now is Rosenberg's the fourth, with Azar, the other two authors. The book was published around 1976. Well, in 1980, around that time, we were involved with the third person who was a very brilliant, bright graduate student named Hal Morgenstern, and we were trying to write another book. It was called Epidemiologic Research that later came out, and people have been using it for many, many years, and a lot of people refer to that as the Bible, although nowadays people like to use Rothman's book, Rothman Greenland instead, but even though came out before that. And we were writing this book. We were right near the end of the book. I'm watching the time. Right near the end of the book, and we wanted to write a chapter in the book about this process that we're going to start talking about is how do you come up with the best model, okay? And we were worried about this because nobody had ever done this. Nobody had ever written that. There are backwards elimination, there were these techniques, but nobody got into this thing about how do you wrestle with confounding and interaction and all of that stuff. And we were a little worried about this. And we started writing that chapter, but it turned out around the time we were starting to write the chapter, we got a visitor from this is in Chapel Hill at UNC, a visit from Nathan Mantell, the famous Mantell and Hansel, the guru guy, And he was well known for basically doing just about everything. So Larry and I had an opportunity to meet with him and came into my office, and it was actually a real brief meeting because what our goal was, other than saying hello and, oogling, or whatever you want to call it, the great man, we wanted to get down to business because we had this question we had. And so we asked Nathan Mantell, we asked him, well, what do you do when you have a complicated situation where you have a lot of variables, you have a lot of data? What do you do? Can you give us a guidelines or a strategy? And this is what Nathan said. It's an art. And he didn't want to tell us anything. And we tried to pin him down a little bit here and there. Well, what if you try this or you try that? No, I know how to do this type of thing. I've been doing it. He also had a very high consulting fee, and he's brilliant. He's done so many great things. But that's what he told us, and it was a short meeting because we never got anything from him. And we were in a position, well, we're going to write something about something that he said was an art, and try to write something about the art when we knew that you couldn't specify a specific mathematical formula for it, but we wanted to say something. And that's what we did. And that turned out to be chapter 21 in this book called Epidemiological Research Principles and Quantitative Methods, published in 1982. But this is also reflected in the chapters in the Logistic Regression book that you're now reading. Chapters, I guess it's 6 and 7, and even chapter 8. It's been sort of transferred into those chapters, and it's really a key thing that you have to know about. And we took a risk, and since then I haven't really felt that what we recommended has been challenged enough for me to change it. And that's what I've been teaching for years. And this is a very important part of this course. Don't you think it ought to be really important? If you think about it, you're doing the study, you got exposure to the disease, you're collecting all this information, and you want to come up with you want to fit a model. What do you do? How do you go about do you just fit one model? So that's what this is all about. Okay. And so, there's all sorts of things I have on this slide. I'm not going to spend a lot of time. There's a rationale for the if you think about what you read in papers, you don't see a lot of information on what the people did when you read a paper, how they did an analysis. They have a method section, and they usually say, well, we did logistic regression. They don't say much more. Well, what did they do? How do you know that they did it well? Okay, well, they might refer to our book, or one of my books is they use this method. That doesn't mean they used it the way I would have wanted them to use it. So it's sort of, so you got this issue. But guidelines are needed. Most importantly, you're going to finish with your MPH, MSPH, PhD, whatever you're going to finish with your degree. You're going to go out in the world, and assuming you're going to stay in the health field and be sort of an epidemiologist type of person dealing with data, you're going to wind up having to deal with models, and you're going to want to worry about this situation and have a perspective on it. And that's what the goal here is doing. So with that, I want to now just start talking about it. Now, I did say there's two goals, validity and precision. And our goal is to talk about validity. That's our focus. And our focus, the reason why validity is because that's what you're really trying to answer. You're trying to do etiologic research more than anything else. And that's why, what's the effect of exposure on disease? What's the relationship? How strong is it? And that's why the goal is more validity than prediction, even though that could be your goal also. Now, here are the 3 stages. I'm looking at the clock because I've got about 5 minutes here. The 3 stages: variable specification, interaction assessment, and confounding assessment, followed by precision considerations. These are the 3 stages. Okay. And they're generally stated, okay? Now, I'm going to talk about each one, what do you do in each one? But let's just, first of all, the list that I've given here, the stage 1, 2, and 3, this is listed in the order in which you should do them. So this is the guidelines. You should do these 3, you can be involved in these 3 stages, and you should do it in this order, okay? Now, the first thing on the list here is variable specification. Why that first? Well, a lot of this is common sense. Variable specification. What model do you start with? Well, you want to make sure that whatever model you start with makes sense given what you're studying and what you know about what you're studying. That's why variable specification is first. You don't want to put variables in the model that don't have anything to do with anything or doesn't make any sense. So variable specification comes first. Then when you start thinking about the model, and let's assume we're doing logistic regression, so the model could have an E variable. It might have more than one E. We'll get to that later. It might have a bunch of V variables, if we're talking about EVW model, then it might have EW variables, which are, the product, the interaction terms in the model. Okay, if that's your starting model, what would you do next, given that you've decided what the initial model is, what's starting out, how you're going to, that has, it's an EV and EVW model. What would you do next? Well, why did I list interaction second, and I didn't list confounding second? Why did I list that second? The reason is essentially if you decide after looking at the model and doing the right thing to look at it, that there is interaction. Now, what I mean by interaction is interaction that the effect of exposure varies with the values or the effects of the other variables you're controlling for. That's what we mean by interaction. I don't mean interaction of two control variables. I mean interaction of the exposure variables with some of the other variables you want to control. If you decide the effect of exposure varies depending upon whether you're male or female, that's interaction, right? And if you decide there's interaction, well, you got to keep these product terms in the model because that reflects the interaction. You got to keep the product term of exposure times gender or sex in the model, because that's telling you the effect is different depending on whether you're male or female. You don't, you got to control for sex, but you don't really want to assess whether sex is a confounder or not, because you know the effect is different depending on whether you're male or female. And you got to put this issue second, okay? And then the third issue is confounding followed by precision, or together, or followed or together dealing with precision. Confounding is where you say, okay, I've assessed interaction. And let's say, for example, there's no interaction. That may happen, but it could be, it's more complicated if there's interaction. There's no interaction, then you've got your exposure variable and the variables you wanted to control for the V's in the model, okay? And you don't have any EVs or EW variables in the model. Well, what do? What you want to say is, well, of these V's in the model, well, do I need a control for all of them? Or can I drop some of them? Well, how do I decide that? Well, the decision has to do with whether they're confounders or not. If they're confounders, I'm going to have to control for them. If they're not confounders, maybe I don't have to control for them. If they're not confounders, well, why might I not control for them? Why might I drop them? Why don't I just control for everything? Well, I mean, I've done my research, I've done my theory, I've looked at the conceptual. Why don't I just control? What might I gain by dropping some variables that aren't confounders? Well, the other thing is precision. It may turn out that you can get the right answer whether you control for a variable or not. You can get a much more precise answer if you drop some variables. That's the reason for the third thing, the third step. Now, which is more important, confounding or precision? This is why I said confounding followed by precision. So I'm just throwing stuff out here. So which is more important? Which do you want to make sure you get? You want to make sure you get the right, Dr. R already talked about this. You want to make sure you get the right answer, as close to the right answer, the most valid answer, or do you want to allow yourself to get a tight confidence interval around the wrong answer? Well, you want to get the right answer. So confounding is more important than precision. But you want to consider both because they sort of trade off a little bit. So that's why this is the third stage. Okay, so that's the three stages. So we're almost done today. So I've already said interaction prior to confounding. I'm going to skip all this because I've just sort of said this, but you can look at these slides. Now, I do say on this slide, interaction may not be of interest. It may turn out that when you start considering what your initial model is, you've decided that given where you are in the study, the kind of study you want to do, I only care whether the exposure is predictive of the outcome and I want to control for confounding, but it's too early to worry about interaction, so I'm not going to want to consider interaction. Well, if that's the case, you just leave out the second step. You have to decide that. So if interaction is not of interest, skip it. But if it is present and it is of interest, you better make sure you consider that first. That's what I'm saying. You following me? And I'm just talking here, but I've been doing this for a while, so confounding followed by precision. I just talked about that. You want to get the right answer, whether confidence is around the wrong. That's what this slide says. Now, the last thing I'm going to say before I quit here is that if you're going to assess confounding, you don't want to do statistical testing to assess confounding. Does that ring a bell? You remember that? Why is that? Why don't you want to do if you're just doing a stratified analysis, you had a variable that you stratified into two strata, you wanted to see if it was confounding. How do you do that? What do? You get an adjusted odds ratio or adjusted risk ratio, and what do? You see whether it's meaningfully different from the crude odds ratio, right? You remember that? Do you do a test to see that? What do? Well, you look at the two, if you see the two numbers, the two odds ratios, if they're really clinically, in some sense, very different, you're going to say, I got to make sure I control for this because I identified a certain variable that needs to be considered, and I get a different answer if I control for it than if I don't control for it. So that's one thing you do, but you don't do a statistical test. The other approach, you remember this thing called the 10% rule? You look at whether there's a meaningful change in the odds ratio, whatever the measure of effect is, when you drop a variable from the model, whether you control for it or not. Well, that's what you have to do when you're doing logistic regression. Logistic regression, dealing with confounding, you're still dealing with confounding. Confounding is an issue about bias. It's not an issue about random error. So even when you're doing logistic regression, you don't do statistical tests to assess confounding. So what do? Well, you do a change in estimate type of thing, but it starts getting complicated when you got a whole bunch of variables in the model. How do you do it? How do you go about doing that? So that's what we're going to talk about. So we're done, okay? That's what today's Tuesday. I start doing this Thursday, and that's what we're going to do, okay? What was the next thing? Oh, okay. Oh.